Okay, our next speaker today will be Kelly Dixon from Mote Marine Laboratory. She'll be speaking about the Spectral Optical model and an updated water clarity reporting tool for Charlotte Harbor seagrasses.
Put your thinking caps on, folks. First, I want to thank my co-author, Mike Wessel, Janicki, and also the Charlotte Harbor Estuary Program, and also the Charlotte Harbor Estuary Program for
and also Charlotte Harbor Estuary for funding this project. It's been really, really exciting to be involved with it. The program has been obviously working with seagrasses to protect and restore them as essential habitat in the estuary for many years. And due to the ephemeral nature of grasses, the deep edges of the grass beds themselves came through that light reaching the deep edges was sometimes insufficient, cause those grasses to retreat. So the emphasis has been looking at water clarity and different things that contribute to a reduction in clarity and how to control those. Earlier models used a linear regression of color, chlorophyll, and turbidity, and the A, B, and C there are just different numerical coefficients. And these worked fairly well, but the application of these models to more recent data, the modeled KD was not matching very well with the measured KD when we were out in the field. And what we began to realize is that with the extremely high color in some of these systems within the estuaries of the different segments of Charlotte Harbor, that we really need a spectral model in order to accurately represent KD. We also began to realize that light is just darn hard to measure while we're out in the field. And so we also realized that if we were able to model attenuation coefficients, or KD, as a function of these different water quality parameters, we could still measure trends in water clarity over time using the modeled KD. I did skip over that first point there, though, that the attenuation coefficient of KD, well, it's a measure of how fast light is removed within the water column. It is one of these backwards parameters where a big number is bad. So a big number of the light is absorbed very quickly within the water column. Before I go on to the spectral model, I do want to talk a minute about the field measurements, because this is truly one of the keys to getting a good spectral model. The sensors that we use in the field measure all wavelengths of light together, irrespective of whether it's red, blue, or green. And then so you'll see when you measure, if you make multiple measurements in the water column, you'll see a smooth progression of light being consumed as you go down through these depths. This lower picture here is light you see is consumed relatively fast, and so that's a high attenuation coefficient, or rather equal. And then since time is money, of course, we don't measure every single one of these depths of light. We'll make measurements in this depth, this depth, this depth, and this depth. And then the law of transformation of those light values gives us our KD value, or our attenuation coefficient. You can also make measurements using a technique where you only make two measurements, and that gives you a perfectly acceptable value of KD. Now, talking about how difficult light is to measure, sometimes you'll get a point that's here instead of here. And then when we will transform and calculate KD from those data, that KD is no longer as what it should be. And so when we're looking for data to calibrate our model against, we want to use data that are in smooth progression, and so we look at the R-squared, or how linear that transform data is, and we use only the best data to calibrate it. So back to the spectral model, we're looking at wavelengths from 400 to 700 across this little range, because that's where plants are used to do. And what I'm showing here are the different components of absorption that are additive and that go into the attenuation of light. And you'll see that the light blue here is the attenuation to the water itself. The green, for instance, this little bump here, and then another little bump here. That's the attenuation due to chlorophyll. There are other spectral shapes that are due to the attenuation due to turbidity, due to dissolved organics or CDOM. And so we add all those up together, and we end up with this red line here, which is the sum of all of the individual components of absorption. And we can use that to calculate a KD for each individual wavelength along this entire range. So we're going to model KD at each wavelength. But another thing is that this shape here, this red line, is going to be different for each different type of water that we get. Each different combination of color, chlorophyll, and turbidity will have a different spectral profile like that. And so that's one of the reasons that this model is so powerful, is it allows us to reflect that. So now we have our KDs for each individual wavelength. Each one. In the model, we shine a standard sunlight spectra onto the water column that we have. We know what our color, chlorophyll, and turbidity are, and we compute how much light reaches the bottom as a function of wavelength. So then we add up all of the upper levels, and we add up all of the light at depth. We're able to calculate a KD that is completely analogous to what would be measured in the field. So when we're calibrating our model, we have 32,000 plus individual light measurements, and that was translated into over 9,000 observations of KD, or the attenuation coefficient. And we're comparing our modeled KD to these observations, but we subselected for the best ones. We also air corrected so that you can have changing incident sunlight while you're making your measurements. You'll affect your readings. So we corrected for that. We also restricted the data to having at least 3 observations or more. Not just using the 2 observations in those red circles when I'm showing you field data a few slides back, because there we don't know whether some of those observations might be compromised. So we only used ones where we had at least 3 data points, and we used deeper stations so that we weren't looking at the light which reflected back off the bottom. We ended up with data of 12 out of 14 discrete segments, and this is the answer. Out of 12 to 14 segments, using the best data, we're looking at the field data, the observed data on the x-axis here. This is our model data. And if you work with light data, it don't get any better than that. And it's the line of organic correlation here between the observed and model data is 0.98, and you can think of that as 98% on your physics test, and you would be happy. The intercept is very close to 0, so that tells us that our model in general is reflecting the measured data in a very accurate way. Now, there were those 2 segments that did not have data, and so we can almost look at that as a model verification, because we didn't participate in, we didn't use those data for calibrating the model. And here are those data. And so you see the scatters are a little bit larger, because there are obviously some of those data that have been affected by bottom reflectance or heavily focusing or karma, whatever. But so these are data that are built from having only 2 observations, and here the slope is still 1.005. And so this is at a completely different location than where the model is calibrated. So this is a very robust result, and it gives us a lot of confidence in the results. We had data. We actually looked at the data from all of the individual segments within the estuary program, from down in Roberts Bay all the way down to the Zero Bay, tidal rivers. And we looked at how that model performed spatially. And these are the plots of the residuals, or the observed KD minus the modeled KD. And what you see there is that there's not a real strong, there's not one segment that doesn't fit very well. There are a lot of outliers here. These 2 segments to the far left, those are the 2 that were filled with only 2 data points. And so there are some of those outliers that obviously are is plus or minus the attenuation coefficient due to pure water alone. And so we're fitting within plus or minus pure water for attenuation coefficient. So again, we were very happy with that. The model, just a few things about the model. It does generate valid attenuation coefficient measurements. These have been validated against a number of other much more complex modeling techniques. It is for optically deep conditions. In other words, it depends on not getting, it simulates not getting any water being collected back up off the bottom. But the really nice thing about it is that it responds directly and exclusively to attenuators within the water column. So it doesn't incorporate bottom collectives. It doesn't incorporate the changes that you'll get when you measure KD and you have a cloudy versus a clear day. You'll get different measurements, even though your water quality or color corridor and turbidity are the same, you'll get a different KD. So the model is not sensitive to that kind of variation, which is good, because that's not what we're trying to model in watershed, to manage within the watershed. So it becomes a really good tool for managing water clarity trends. So now we're ready to use the model. We have water quality data from 98 through 2011, and we modeled our KD using color corridor and turbidity. And then we went back to the water clarity estimation tool and scoring that Janicki and Corrine and Wessel had developed earlier. And while previously they used measured KD, we're going to use modeled KD in exactly the same procedure. We're going to compare our modeled KD during each individual year to a reference period that had been previously selected as 2003 to 2007. And so here's an illustration of the cumulative distribution curve of KD in a particular segment. This one is lower limit A during our reference period of 2003 to 7. And you arrange all the data in order, and this is what it looks like. And this is the 30th percentile, and this is the 70th percentile. And these are just where the value of the KD at which 30% of the data are less. That's how those are defined. Now we're taking individual year's data and we compare it to this reference period. And so here's the made-up data, and all of these data are a lot worse. This would be really dreadful. But by the 30th percentile of our made-up data being higher in KD, or worse water clarity, we give that a score of -1. Over here by 70th percentile, this one's worse also. This one also is a score of -1. And the sum of these two scores gives us a total overall score of -2. And then, so then if your water quality are better, you would get a +1. That kind of thing. So for each year, we're going to compute that numeric score. In that example, it was a -2. And so then we're going to look at how this relates to our seagrasses. And remember that our different segments have been assigned either a protection or a restoration category based on seagrass presence and the amount of acres and how much we would like to have there. And so for protection, we want to keep the water clarity that we got during that reference period. Whereas in restoration, we know we want more grasses, we know we need to improve the water clarity relative to that reference period. And then when we assign color coding to our individual scores, the individual years, that's going to be different depending on whether it's restoration or protection. And it really is just calling different amounts of attention based on what we know we need to accomplish within that particular segment. So here's a tiny print that no one can read, but it's a lot easier than looking at 32,000 data points on here. You have the restoration segments over on this side. Each one of these columns is an individual estuary segment. The rows are right here from 98 to 2011. And over here are the protection target segments. Same thing, years. And if you'll see that these numbers here are 2, 1, 0, -1, and -2. And so for protection targets, where we want to just keep the water clarity we have, anything that's at 0 or better, we're okay with. If it's a little stable or a -1, then we know we want to look at that more, and we certainly want to look at it if it's a -2. And so that they're different color codings are just to draw different amounts of attention of people looking at these data in order to see what's going on.
And you can see that there are some seasonal signals here. The 2007 drought, everything was really great. 2005, a lot of rainfall, a lot of flow, a lot of high color, a lot of reduced color clarity. That doesn't show up as much here, in part because of the different color codings, the protection targets. So our next step with this approach is to we can link this scoring to seagrass performance, actually look at the acres and change over time. The 30th and 70th percentile are somewhat arbitrary selection just to capture most of the data. It could be that there are other percentiles or more percentiles that might be a more sensitive tool, but mostly this technique is something that we can use to monitor over time. And even if the monitoring design changes, we have the ability to go back and calculate new distribution curves, those new cumulative distribution curves for the reference period, and we can go forward with any type of monitoring program. And that is it. And I just want to thank you all for your attention.
Well, we certainly have time for questions. If you'd like to ask a question, please step up to the mic. I'm going to turn my back, see if I have a question.
It seems like a really useful management tool is I'm glad you pointed out that water clarity differs between dry years and wet years, because some of our most healthy watersheds are actually going to give a lot of highly colored water creation. Does your tool here allow us to be able to predict how much we could improve water clarity by reducing chlorophyll, knowing that we have given it sort of background color concentrations, and then tweak out the chlorophyll effect?
Yes, you could take the data set that we have, and let's say you had a goal of reducing chlorophyll by 10%. You could artificially multiply all of your chlorophyll data by 29, rerun that, and compare that distribution to the original distributions. Does that answer your question?
Yes, it does.
Okay. So you can do the same thing with color and turbidity. The thing about it is, though, since it's combined in such a complex way, and I only showed you absorption, there's also scattering, sun angle, and some other magic math things that are happening all underneath. So you can't just set chlorophyll to 0 and say, well, that counts for 30%, or turbidity to 0, because they're interrelated, and some of the functions are cross-related in that the scattering and turbidity also has chlorophyll components to it. So it's not as simplistic as using one of the linear regression models.
Any more questions?
Kelly, as you have been developing this model based on water quality characteristics, turbidity, and see how, has anything come to your mind about possibilities to improve the way we are collecting those constituents currently that would
You were going to say, has anything come to light?
As we continue to monitor water quality, for instance, would it benefit from different depths or any logistical things that you must consider to continue this work and refine it each one possible?
The model definitely takes a single sample that's been collected for color, chlorophyll, and turbidity. And it assumes that those conditions extend over the entire water column. For most of our estuaries, for most of the time, that's an accurate assumption. When it's not an accurate assumption is when there's a big freshwater inflow in the head part of Charlotte Harbor, and you'll get really dark water on the surface and saline water on the bottom. Generally, at those times, the amount of white that's produced in the upper portion is so complete that the amount of light that would be transmitted in the lower portion, while it might be a large fraction of the total, it's 1 or 2 photons. It's years out of 2,000. And so the
illuminate you much on very few occasions, and it would be the difference between 0.1% light at the bottom or 0.11% light at the bottom. So it's a little bit. Probably the biggest thing that would help when you're calibrating a model like this is to first of all have lots of data on the brain, but to also have your light data that you measured, have really high quality light data measured with multiple depths, with multiple observations, and with long integration times.
Did you mention that this is going to be from the water atlas for people to...
Oh, sure. Sorry, I should have said that. This model will be used with the monitoring data and will be incorporated into the water atlas so that water atlas will also present a model KD value, and that's where this will come from this model. The Estuary program itself will have the model itself to use, and so doing things like Sid was talking about multiplying all your 4 built on 0.9, so they'll be able to do those kinds of things.
Thank you, Dr. Dixon.